When we use large language models, there is another parameter we often encounter called temperature, also known as temperature scaling. How does temperature affect the output of large language models? Let's explore this through a video. First, we have a prompt. How are you? Next, we want the large language model to generate a response. The generation logic is as follows. Using the large language model, we compute the meanings of each token in the input, represented as vectors. Our task is to generate tokens following the question mark. For this, we introduce a module that outputs a probability distribution for the next token. Within this probability distribution, tokens with the highest probability are more likely to be sampled as the next token. During the sampling process for the next token, based on the probability distribution, we use parameters like top P and top K to narrow the range. Through top P and top K, we pre-filter the token set, discarding those unlikely to appear in the current position. We retain only the most probable few hundred tokens. For the next sampling step, the temperature parameter, however, affects this module directly, altering the shape of the probability distribution. With different temperature settings, the resulting probability distributions take different shapes. To understand this, consider a simple example. Suppose we have a six-dimensional vector, 1, 1, 1, 2, 2, 2. We want to convert this vector into a probability distribution where the sum of all probabilities equals 1. Currently, the sum of the vector values is 9. So one simple approach is dividing each number by 9. However, this approach is not ideal in AI applications. Instead, we use a method called softmax. For each vector value xi, we compute exi and divide by the sum of all exi values. The same applies to all other values. Using this method, we obtain a normalized probability distribution. Applying this to our example vector, numerator e1 and e2, denominator 3e1 plus 3e2. The resulting probabilities are approximately 0.09 to 0.24. This probability distribution can be visualized as a bar chart. Probabilities for the first three tokens are 0.09 each. Probabilities for the last three tokens are 0.24 each. Now, introducing temperature, we modify the softmax equation to include T where T is the temperature. If T equals 0.5, dividing xi by T scales up the values. For example, 1 divides 0.5 equal 2. So E1 becomes E2, and E2 becomes E4. When T less than 1, the distribution sharpens, concentrating probabilities on a smaller set of tokens. For example, if T equals 0.5, the new probabilities might be 0.04 to 0.29. Conversely, if T greater than 1, the distribution flattens, reducing differences between token probabilities. If T equals 2, the probabilities become smoother, increasing diversity in the generated tokens. Adjusting temperature allows us to control the balance between diversity and consistency in output. Lower, more focused, less diverse output. Higher, T, more diverse but potentially less coherent output. In summary, the temperature parameter directly controls the diversity of the generated output by shaping the probability distribution.